Good evening or good morning. This course will be about a second type of ordinary differential equations solved by substitutions and a well-known type of ordinary differential equations, namely equations of homogeneous type. But first, let us look at one more example of a Bernoulli type ordinary differential equation, and then let's solve an initial value problem for this equation. The equation that we're looking at is y prime plus y is equal to x y to the minus 2, or x over y squared. This is clearly an equation of Bernoulli type. It looks very similar to a linear equation, but because we have y to the minus 2, it's actually a Bernoulli type equation. So it fits the general formula y prime plus some coefficient times y is equal to another coefficient times a power of y. Here the coefficient of y is 1 and the coefficient of the power of y is x. The power of y is n is equal to minus 2, so when solving the equation we should use the substitution u is equal to y to the power 1 minus n, which is 1 minus minus 2, so it's y to the third power, y cubed. Well, if u is y cubed, then y is the cubic root of u, or u to the power 1/3, and then by the chain rule, when we differentiate y, we get y prime is 1/3 u to the power minus 2/3, and then times du over dx, because u itself is a function of x. So now that we have y and y prime, we can completely replace y by u in the equation. So let's do the replacement. Y prime is 1/3 u to the minus 2/3 u prime, and then plus y, which is u to the power 1/3, is equal to x times y to the minus 2. So this is u to the power 1/3 raised again to the power minus 2, or u to the power minus 2/3, because the powers multiply. 1/3 times minus 2 is minus 2/3. So notice that we have 3 powers of u in the equation. We have u to the minus 2/3, then u to the power 1/3, and again u to the power minus 2/3. So 2 of the powers are the same. This is because our substitution worked. And now we multiply the whole equation by u to the power plus 2/3, and this cancels the 2 powers that were u to the minus 2/3. And we get the equation for u, which is 1/3 u prime plus u is equal to x. So u to the power 1/3 times u to the power 2/3 is equal to u. And now we see that this is indeed, as it should be, a linear equation for u. So indeed we have a linear equation for u as it should be, 1/3 u prime plus u is equal to x. But this equation is not in standard form because u prime is not by itself. We have 1/3 u prime. So in order to solve it, let's first bring it to the standard form by multiplying the whole equation by 3. So we get u prime plus 3 times u is equal to 3x. Now that the equation is in standard form, we can correctly compute the integrating factor. The coefficient of u is 3, so the integrating factor is mu of x is e to the power integral of 3 dx. So it's e to the power 3x. We'll multiply the equation by the integrating factor and get e to the 3x u prime plus 3e to the 3x u is equal to 3x e to the 3x. But because we chose the correct integrating factor, of course, now both terms on the left-hand side of the equation combine and give the derivative of the product e to the 3x times u. So when the derivative falls on e to the 3x, you get 3e to the 3x times u. When the derivative falls on u, you get e to the 3x u prime. So this works out. The whole left-hand side is e to the 3x times u, everything prime. So the equation has become e to the 3x u, everything prime, is equal to 3x e to the 3x. We integrate both sides as a function of x. On the left-hand side, the integral of the derivative is just what was under the derivative, so it's just e to the 3x times u without the prime. And on the right-hand side, we have to compute the integral of 3x e to the 3x. And we do this by an integration by parts and get that it's equal to x e to the 3x minus e to the 3x over 3 plus a constant. So we have e to the 3x u is equal to this expression. So let's divide by e to the 3x to obtain u. And we get u of x is equal to, well, e to the 3x cancels, and we get x minus 1/3, and then plus a constant times e to the minus 3x, because the constant did not contain e to the 3x, and then dividing by e to the 3x is the same as multiplying by e to the minus 3x. So we have u of x is equal to x minus 1/3 plus constant times e to the minus 3x. But we want to obtain the solution in terms of y, because y is the unknown in the original equation. And we remember that y was u to the 1/3. Let's have a look. Right, so notice that y is equal to u to the 1/3. So the general solution is y of x is equal to x minus 1/3 plus a constant times e to the minus 3x. Everything raised to the power 1/3. So now let's solve an initial value problem for this Bernoulli equation. So let's consider the initial value problem consisting of the equation y prime plus y is equal to xy to the minus 2, together with the initial condition y of 0 is equal to 2. Since we have already computed the general solution of the ordinary differential equation, we can use it here. So the general solution is y of x is equal to x minus 1/3 plus any constant times e to the minus 3x, everything raised to the power 1/3. Now we need to compute the constant, so plugging in 0 for x and 2 for y of 0, which is y of x, when x is 0, we get 2 is equal to 0 minus 1/3 plus the constant, everything raised to the power 1/3. So let's raise this to the power 3 to cancel out the power 1/3, because 3 times 1/3 is 1. And we get that 2 to the power 3, which is 8, is minus 1/3 plus c. So the constant c is 8 plus 1/3, which is 25/3. So we found the value of c that corresponds to the solution of this initial value problem and to the initial condition y of 0 is equal to 2, as you can check. So the solution of the initial value problem is y of x is equal to x minus 1/3 plus 25/3 times e to the minus 3x, everything raised to the power 1/3. Finally, let's talk about homogeneous type equations. In order to see what homogeneous type equations are, we must first define homogeneous functions. So homogeneous type equations are not related to the homogeneous equations we talked about in the linear case. The homogeneous type equations that we study in this course, today, are very nonlinear. So these are two different ways in which the word homogeneous is used. The homogeneous equations we study today are related to homogeneous functions. What is a homogeneous function? A function of two variables, f of x and y, is called homogeneous of degree n if for any positive number t, f of tx and ty is equal to t to the dn times f of x and y. So homogeneous functions are to some extent related to polynomials, but the degree of a homogeneous function does not have to be a positive integer like for a polynomial, or it does not even have to be an integer at all. Actually, the degree can be a negative number like -1, -2, or it can be a non-integer like 1.5 or pi or minus square root of 2. So here are some examples of homogeneous functions. Some homogeneous functions actually are polynomials. For example, let's start with the first two examples here. X squared plus xy plus y squared is a homogeneous function of degree 2. Notice that the degree of every term is 2. X squared has degree 2. X times y has degree 2 because the degree of x is 1 and the degree of y is also 1. And together the degree of x times y is 2. And the degree of y squared is also 2. Similarly, x cubed plus 2x squared y is a homogeneous function of degree 3. And again, it is a polynomial in two variables. The degree of x cubed is 3, and the degree of x squared y is also 3 because the powers add up to 3. You can also have homogeneous functions of negative degree. For example, 1 over xy squared plus 1 over x squared y. Both terms have degree -3 because the powers add up to -3. So 1 over x has power -1, the degree if you want. So it has power -1, and 1 over y squared has degree -2. So it adds up to -3. And same for 1 over x squared y. Or this is a more complicated example, I guess. 1 over x squared plus 1 over xy plus y squared is again homogeneous of degree -2. Just notice that all the terms in the denominator have degree 2, So it satisfies the definition of a homogeneous function with degree -2, because those are in the denominator. Square root of x plus square root of y is a homogeneous function of degree 1/2. So again, we can have non-integer powers. Square root of x has power or degree, if you want, 1/2. And it's times no power of y, so the total degree is 1/2. And same for square root of y, has degree 1/2, and it's times no power of x, so it has degree just 1/2. And homogeneous functions can be very simple. In particular, linear functions like this, 2x plus y, that don't contain a free term, are homogeneous of degree 1. On the other hand, if we had 2x plus y plus 1, this would not be a homogeneous function because the plus 1 would have a different degree. Here are examples of a different nature. So x squared plus y is not a homogeneous function because x squared has degree 2 and y has degree 1. So the degrees don't match. E to the x plus e to the y is not a homogeneous function because these homogeneous functions should involve powers of x or of y. So e to the x sine of x cosine x are not going to be homogeneous of any degree. And finally, x plus y squared over x is homogeneous of degree 1. The first x has degree 1, and in y squared over x, y squared has degree 2, 1 over x has degree -1, and 2 added up with -1 gives 1. So y squared over x again has degree 1. So now finally, how does this tie to homogeneous type equations? A homogeneous type equation is an ordinary differential equation that can be written in the form y prime of x is equal to a homogeneous function m of x and y divided by another homogeneous function n of x and y, where m and n are homogeneous of the same degree. And instead of writing it as a fraction like this, we could write y prime as dy over dx and cross multiply, and formally, in differential form, an ordinary differential equation is of homogeneous type if it can be written as m of x and y dx plus n of x and y dy is equal to 0, and m and n are homogeneous functions of the same degree. And notice that the m and n in this definition are not the same as the m and n in the fraction above, because there's some missing minus sign. So here are some more examples of equations of homogeneous type this time. First, y prime is x minus y over 2x plus y. All the terms that appear in the equation, both in the denominator and in the numerator, are of degree 1. So both the denominator and the numerator are homogeneous functions of degree 1. So the equation is of homogeneous type. Okay, y prime is equal to square root of x plus square root of y over square root of x plus y is again a homogeneous equation because all terms have degree 1/2, as you can check. So square root of x, square root of y, and square root of x plus y are all three of them homogeneous functions of degree 1/2. So both the denominator and the numerator are homogeneous functions of degree 1/2. So the equation is of homogeneous type. And here are two equations written in differential form. x squared minus y squared times dx plus 2xy times dy is equal to 0. Clearly, all the terms have degree 2. And x squared plus y squared times dx plus 2xy times dy is equal to 0. This equation is both of homogeneous type and exact. Unlike the previous one, which was just homogeneous, but it was not exact. So all these types can have overlap. An equation which is homogeneous can be separable or linear or exact, or why not even of Bernoulli type as well. And here are a couple of examples of equations which are not homogeneous. So y prime is equal to x minus y over 2x squared plus y. Here all the terms have degree 1 except for 2x squared, which has a different degree, namely 2. So 2x squared plus y is not a homogeneous function of any degree. And x squared plus y squared plus 1 dx plus 2xy dy is equal to 0. Here, the plus 1 does not match the degree of the other terms. So x squared plus y squared plus 1 is not a homogeneous function. And again, the definition also requires that the functions should be homogeneous of the same degree. So here, this would be satisfied if it weren't for 1, because x squared plus y squared would have degree 2, and 2xy also has degree 2, but the plus 1 has degree 0, so every constant has degree 0, maybe except for the number 0, which has degree minus infinity. So this is not a homogeneous type equation. All right. So how does one solve homogeneous type equations? One always uses the same method, the same substitution, namely y of x is equal to some new unknown function u of x times x. Or in other words, instead of solving the equation for y, we try to solve it in terms of this new unknown function u, which is the ratio, the quotient y over x. So it's always the same method. Instead of solving the equation for the unknown function y, we solve it for a new unknown function u, which is equal to y over x. This has the effect of transforming every homogeneous type equation into a separable equation. So in the new unknown function u, this will always be separable equation. And we can solve it by the same method that we use to solve separable equations. So how does the substitution work in the equation? If y is equal to u times x, then we also need to know what y prime is. And y prime is equal to, by the product rule, so u times x is the product of two things, u and x. So it should be u prime times x plus u times the derivative of x. But the derivative of x as a function of itself is 1. So y prime is equal to u prime x plus u. So let us prove that this substitution always works. Consider any homogeneous type equation, y prime is equal to m of x and y over n of x and y. And let n be degree of both m and n. So m and n are supposed to be homogeneous functions of the same degree. This is a homogeneous type equation. Okay, so in this equation, we divide both the numerator and the denominator by absolute value of x to the n, where n is the degree of these homogeneous functions. Then the coefficients actually will become functions of only y over x, not of y and x separately. So this is the reason why we pick u to be y over x, because we can do this. Notice that this may not work when x is equal to 0, because we cannot divide by 0. So we will do this separately for x bigger than 0 and x less than 0. And at the point x is equal to 0, the equation probably needs a special treatment. And then, well, let's look at one of them. So if m of x and y is a homogeneous function of degree n, then we can factor out absolute value of x from both x and y, and m of x and y is equal to absolute value of x to the n times m of x over absolute value of x and y over absolute value of x. So this is absolute value of x to the n because m is homogeneous of degree n. So here, absolute value of x plays the part of t in the definition of a homogeneous function. And then x over absolute value of x is plus or minus 1, according to whether x is positive or negative. And y over absolute value of x is also always plus or minus y over x, because absolute value of x is plus or minus x, according to whether x is positive or negative. So we can do the same for capital N, which is again a homogeneous function of x and y, and then I get a factor of absolute value of x to the n, both in the denominator and in the numerator, and it cancels. So we get that y prime is equal to nothing but some function of y over x, where the function depends in this complicated way on capital M and capital N that we started from. Namely, it's capital M of 1 and y over x over capital M of 1 and y over x when x is positive, and capital M of minus 1 and minus y over x over capital N of minus 1 and minus y over x when x is negative. So either way, it's just some function of y over x. And we have reduced the equation, so we can always do this to a homogeneous type equation to y prime is equal to some function of y over x. So then if we can do this, then let's use y over x for our new unknown function u, as I announced in the beginning. So let's u is equal to y over x. In other words, let y over x is equal to u of x times x. So then y is equal to u times x, and y prime is u prime x plus u. And then we substitute y prime with u prime x plus u. Then we replace f of y over x with f of u, because y over x is u. Okay, so the equation becomes u prime x plus u is equal to f of u. Then let's subtract u from both sides and we get u prime x is equal to f of u minus u. And then we can divide both sides by x and we get that u prime is equal to 1 over x times f of u minus u. Well, this is clearly a separable equation because on the right-hand side, we have a function of x, which is 1 over x, times a function of u, which is f of u minus u. So we can solve this separable equation to find u. And then we want to solve the equation in terms of the initial unknown function, but y of x, which was the original unknown function, is just u times x. So we take u that we found as the solution of this separable equation, and we multiply it by x, and that is the solution of the original equation. And this is it. Now let's look at a couple of examples and see how hard the separable equation is to solve. All right, here's one example. Consider the ordinary differential equation y prime is equal to y squared over 2x squared plus xy. Here the degree of every term, both in the denominator and in the numerator, is 2. So both y squared and 2x squared plus xy are homogeneous functions of degree 2. So this really is an ordinary differential equation of homogeneous type. When solving these equations in practice, one can always start with a substitution. Y is equal to u times x. And then y prime is equal to u prime x plus u. So let's replace y prime and y in the equation. And we get, so instead of y prime, we have u prime x plus u is equal to ux quantity squared over 2x squared plus x times ux. Okay. So now in the fraction, everything contains x squared. So on top we have u squared times x squared. On the bottom we have 2x squared and then plus x squared times u. So everything contains x squared, and we can simplify this fraction by dividing everything by x squared. So we're left with u squared over 2 plus u. This is an important feature of homogeneous type equations. If everything works out correctly, then at this point the fraction should be only a function of u, as I mentioned in the general proof. So it should be u prime x plus u is equal to some function of u. So here we have u prime x plus u is equal to u squared over 2 plus u, which is a function of u indeed. And let's subtract u from both sides, as I said before. And we get that u prime x is equal to u squared over 2 plus u minus u. And then computing this expression, we have u squared minus 2u minus u squared over 2 plus u, after bringing everything to the same denominator. So we get minus 2u over 2 plus u. So we got this separable equation, u prime x is equal to minus 2u over 2 plus u. This is clearly a separable equation, and we should try to separate it by putting all the terms containing, all the factors containing x on one side and all the factors containing u on the other side. So dividing both sides by x and multiplying by 2 plus u over 2u in order to cancel the fraction, we get 2 plus u over 2u times u prime is equal to minus 1 over x. So after dividing by x and multiplying by this fraction to cancel 2u over 2 plus u, on the right-hand side, we are just left with minus 1 over x. So the equation is 2 plus u over 2u u prime is minus 1 over x. Now, the equation is separated, so integrating both sides as a function of x leads to integral over 2 plus u over u prime dx is equal to integral of minus 1 over x dx, which is minus natural log of absolute value of x plus a constant. And in the left-hand side integral, as usual, we make a change of variable from x to u, which is u of x. So let u be our new integration variable. And then u prime dx is the same as du. And the integral becomes integral of 2 plus u over u du, which is nothing but twice natural log of absolute value of u plus another constant. So twice natural log of absolute value of u plus u is going to be equal to minus natural log of absolute value of x plus the difference of the two constants. So this is what we have. Twice natural log of absolute value of u plus u is minus natural log of absolute value of x plus a new constant, C3, which is the difference of the previous two constants. And now, since u was y over x, let's replace u by y over x in the equation. Then natural log of absolute value of u will be natural log of absolute value of y over absolute value of x, which will be the same as natural log of absolute value of y minus natural log of absolute value of x. So 2 times that plus y over x is equal to minus natural log of absolute value of x plus a constant. And this is the general solution of the equation in implicit form. Unfortunately, we cannot really solve this equation for y. I mean, there is no explicit formula which gives y as a function of x from this. We could simplify it a bit further. For example, we could group all the natural log of x together or do things like that, but this is more or less the final answer. And notice that when I solved our separable equation for u, we missed one solution. Namely, when I multiplied by 2 plus u over 2u to cancel the fraction 2u over 2 plus u, we can only do that when u is non-zero. So we missed the possibility that u could be zero. Why did we do that? Because that's how we solve separable equations, but it turns out that u can very well be zero. Let's examine this possibility. If u of x is the constant function 0, then y is u times x. So 0 times x is 0 as well. So y is also the constant function 0. And notice that if you plug the constant function 0 into the equation, it is a solution, because if y is 0 in the equation, then the fraction on the right-hand side is 0, and then y prime is also 0 because the derivative of a constant function is 0. So this is a solution that we had missed. So in addition to the general solution described before, we have one extra solution, the constant function y of x is equal to 0. All right, here's one more example of an equation of homogeneous type. Y prime is equal to x cubed plus y cubed over x y squared. All the terms in the fraction, both in the denominator and in the numerator, have degree 3. So the degree of xy squared is 3 because x is to the power 1 and y squared has power 2 of y. So this is degree 3, and obviously x cubed and y cubed have degree 3. So this is an equation of homogeneous type because both the denominator and the numerator have degree 3. Now, let's again use the substitution. Y is equal to u times x, where u is a function of x. So y prime is equal to u prime x plus u by the product rule. Making these substitutions in the equation, we get u prime x plus u, this is instead of y prime, is equal to x cubed plus u times x cubed, this is instead of y cubed, over x times ux quantity squared. And again, notice that all the terms in the fraction contain x cubed. So we can simplify the fraction by x cubed, and we get 1 plus u cubed over u squared, which is the same as 1 over u squared plus u. So u prime x plus u is equal to 1 over u squared plus u. All right. So the u cancels, and we are left with u prime x is equal to 1 over u squared. Very clearly, this is a separable equation. U prime x is equal to 1 over u squared, and we have to divide by x and multiply by u squared to actually separate the equation. And we get u squared u prime, so that's after multiplying by u squared, is equal to 1 over x. That's all that's left on the other side after we divide it by x. So we get integral of u squared u prime dx is equal to integral of 1 over x dx. Integral of 1 over x dx is natural log of absolute value of x plus a constant. And the integral of u squared u prime dx, we make the change of variable from x to u again, which absorbs u prime, and we get integral of u squared du, which is u cubed over 3 plus another constant. And then we only record, it's enough to record the difference of the two constants. So u cubed over 3 is equal to natural log of absolute value of x plus the difference of the two constants. Okay. So now let's multiply the whole equation by 3. We get u cubed is equal to 3 times natural log of absolute value of x plus a new constant, which is 3 times the old one. So C2 is 3 times C1. And then let's take the cubic root, or let's take the whole equation to the power 1/3, and we get that u is equal to 3 natural log of absolute value of x plus a constant, everything raised to the power 1/3. So finally, since we know u of x, we remember that y was equal to u times x. So y is 3 natural log of absolute value of x plus a constant, everything raised to the power 1/3 times x. So this is what I like about homogeneous type equations, that you can get these sorts of solutions. Now let's finally solve, as an example, an initial value problem based on this equation. So let's consider the equation y prime is equal to x cubed plus y cubed over x y squared with the initial condition y of 1 is equal to 2. We already found the general solution of the equation. Y of x is equal to 3 natural log of absolute value of x plus a constant raised to the power 1/3 times x. And then now we have to find the constant. So plugging in 1 for x and 2 for y of x, so y1 should be 2. We get that 2 is equal to 3 times natural log of absolute value of 1 plus the constant raised to the power 1/3 times 1. But natural log of 1 is 0, so that part goes away. And multiplication by 1 also goes away. So we get that 2 is equal to the constant raised to the power 1/3. Then the constant should be equal to 2 raised to the power 3, so it's 8. And then the solution of the initial value problem is 3 times natural log of absolute value of x plus 8, everything raised to the power 1/3 times x. So this is the solution of this initial value problem that we obtained by plugging in the initial condition and computing the constant c. And we got that c was 8. And finally, this problem on this page is left as an exercise. If you want, you can think about it. If not, we'll probably do it in class on Monday. Y prime is equal to x squared plus xy plus y squared, all divided by x squared plus xy. Thank you for your attention. If you want, you can think about this example. If not, we'll do it in class on Monday. And again, thanks for your attention and have a great day.